I'm Jeff Groh, and this is Partial Differential Equations. Last time, we talked about Fourier series. If you have some function f and a collection of orthogonal functions, en, then the Fourier series relative to this basis would be the sum as n goes from 1 to infinity. You project f onto each of these elements, and then add up those projections. An important question is, do you retrieve the function f? It's like saying in order to get from point A to point B, you go a certain number of units one way and a certain number of units in an orthogonal direction, and that way you can get from point A to point B. That's exactly what's going on here. As a simple example, we can take the standard order basis in R3 and an arbitrary vector v. If we take the dot product of v with this first basis element, E1, then we'll get x. The dot product of E1 with itself is 1, and then we multiply by E1. To that we may add the dot product of v with E2, which is y. This is 0. And the dot product of v with E3, which is z. And sure, when we project v onto each of these three orthogonal directions and add that up, we recover the original vector. However, we saw that with respect to our function 0 less than or equal to x is less than or equal to 1/2, and 1/2 is less than x is less than or equal to 1, and projecting onto the basis cosine 2 pi nx sine 2 pi nx, that our functions, approximating functions, were something like this, where there was a little bit of overshoot, illustrating the Gibbs phenomenon on each side. When you take partial sums of the Fourier series representation, each partial sum passes through a height at 1/2, and hence the limit will pass through at 1/2. So we do not get conversion of the sequence of partial sums at the point x equals 1/2, converges to the wrong value, 1/2 and not 0. We don't get pointwise convergence, but we do get convergence almost everywhere. When convergence is within every point in a set except possibly a set of measure 0, we say that convergence is almost everywhere. We do get convergence almost everywhere, and if we adopt the principle that functions are contained in equivalence classes, they're equivalent if they differ on no more than a set of measure 0, then we get convergence in some sense. We'll talk about that a little more. Functions are in L1 if their integral over the domain that you're working on of the absolute value is finite. They're in L2 if the integral over some domain that you're interested in of the absolute value of the function squared is finite. These two sets of functions are important in the present context because of the so-called one norm. This is just the integral over your domain, and the two norm. which is the square root of the integral over your domain of the absolute value of the function squared. These end up being norms, so you can calculate distances. Note that the 2 norm is the square root of the inner product of f with itself using the L2 inner product. There are different kinds of convergence that are important. We say that the functions fn converge to f pointwise if for each x in the domain of f, of the fn's, we're assuming the fn's and the f have a common domain, then fn of x converges to f of x in the usual sense of a sequence of numbers. We can see that our sequence of partial sums for the Fourier series of this little digital bump wave do not converge pointwise at x equals 1/2. You have the wrong point at which they converge to. So we don't get pointwise convergence there. There is another form of convergence, pointwise almost everywhere, and so that would be pointwise everywhere except on a set of measure 0. So if fn converges to f pointwise except on a set of measure 0, we say fn converges to f pointwise almost everywhere. Or sometimes we'll just say almost everywhere. On the other hand, we say that fn converges to f in the mean or we'll just write mean if we take the limit as n goes to infinity of the integral over this domain of the absolute value of fn minus f, if that limit is 0. Notice that integrals are averaging processes. The average height of a function is defined in terms of an integral. And so when we take the limit of the integral of the difference of these two functions, the integral will ignore what happens on very small sets of measure 0. And so you get convergence in the sense of this L1 norm, if you will. This is also written, the limit as n goes to infinity, fn minus f in the 1 norm. If that's 0, then we get convergence in the mean, or we can just say L1 convergence. L2 convergence is also important in the present context. We're assuming that our functions are elements of the vector space L2 in the sense that each of these vectors must have an inner product with itself that is finite. We're defining that inner product to be the integral over some domain, En of x, and then times En of x. So we're squaring the function and integrating. We're assuming you get a finite result for each of those. After all, these are supposed to be normalizable. The functions that we deal with in this course must both be largely integrable and square integrable. They must both be elements of the vector space L1 and L2. There are theorems in more advanced real analysis settings where we learn things like the Fourier inversion theorem and Plancherel's theorem, whereby in various special cases we do get convergence, but usually not pointwise convergence. We'll get convergence of the Fourier series in the sense of L1 or L2. For our purposes here, the functions that are well represented by Fourier series are going to be those that are piecewise continuous, for sure. Those have no worse than a finite number of jump discontinuities on a finite domain. If the domain is infinite, we assume that piecewise continuity means a finite number of jump discontinuities on any finite subset of the domain. That way, the discontinuities can't have a point of accumulation, but we're still allowing there to be an infinite number of discontinuities, just a finite number on each finite subset of the domain. We're going to establish this Fourier representation for periodic functions first. You recall that a function is periodic if f of x plus k equals f of x for all x, and the smallest positive value of k is the period. So, for instance, we know that sine of x plus 4 pi is the sine of x, but 4 pi is not the period. 2 pi is the period. Four pi is not the smallest value, positive value, that causes the function to repeat. In our last lecture, we looked at the Fourier basis 1 cosine 2 pi nx sine 2 pi nx, but we were constrained to the interval 0, 1. Today, we want to look at the interval negative L to L, in which case we'll need to modify this a little bit. We'll divide by the interval length, yielding a slightly different potential Fourier basis. We can prove orthogonality in much the same way that we did in the last lecture. What is needed is normalization. So in particular, when we take the inner product of 1 with 1, we get 2L. Note that this is the norm of 1 squared, which means to normalize, we divide by the norm, we need to divide by the square root of 2L. Also, if we take one of our cosines and the inner product with itself, we'll have cosine squared, to which we apply a half angle identity, the last term is 0 because we'll have an integer number of periods cycled through the interval from negative L to L. It follows then that the integral is 2L multiplied by 1/2, we get L. That's the norm of one of our cosines squared. Again, to normalize, we'll have to divide by the square root of L. It should be clear that if we used the sine functions instead, the only thing that would differ is that we would have a minus. And on that term, we get an integral of 0 anyway, so we still get L. Our Fourier basis then, that has been normalized, is 1 over the square root of 2L, 1 over the square root of L, cosine pi n x over L, 1 over root L, sine pi n x over L as n goes from 1 to infinity. However, it may be easier to write our Fourier representations without normalizing. Note that the denominator here is the norm of En squared. Our Fourier representation in this case will be 1 over 2L. We'll integrate the function up against the number 1 plus the sum as n goes from 1 to infinity. We'll have an cosine of pi n over Lx plus bn sine pi n over Lx. And the an's and bn's come from this representation. We have then an will be 1 over L, the integral from minus L to L, of our function times the cosine of pi n over Lx. And bn will be 1 over L, the integral from minus L to L, f of x times the sine pi n over Lx. Let's do an example. Suppose my function is e to the power of x, restricted to the interval minus L to L. The constant a naught is 1 over 2L, integral from minus L to L, of 1 times e to the x. This gives the antiderivative of e to the x is e to the x. Evaluate the endpoints and subtract. We'll have e to the L minus e to the minus L over 2. And this is the hyperbolic sign of L. For those of you who don't remember, the hyperbolic sign is, by definition, and definitions you accept, you don't prove them, you accept them, it's e to the x minus e to the minus x over 2, and the hyperbolic cosine is, because I said so, e to the x plus e to the minus x over 2. These hyperbolic trigonometric functions have some very important properties, like hyperbolic cosine squared x minus hyperbolic sine squared x equals 1, looking more like a hyperbola than a circle. And so the circular functions would have a plus, the hyperbolic functions have a minus. Let me record over here that our constant a naught is the hyperbolic sign of L divided by L. An will be the inner product of our function e to the x with the cosine pi n over Lx. That's divided by the inner product of this with itself, which ended up being L. So we get 1 over L times the integral from negative L to L, e to the x cosine pi n over Lx. Now, how do we integrate an expression like this? This is definitely going to apply integration by parts, but it's going to use that technique where you use integration by parts twice, end up with an expression involving this original integral, and then you have to move to the other side, divide by the coefficient to finally solve for the integral. The way this works, as with all integration by parts, you have a u and a dv that you identify. We're going to identify cosine of pi n over Lx as the u and e to the x as the dv. You take a derivative down the first column and integrate down the second column. When we differentiate here, we'll have minus pi n over L times the sine of all that same stuff. And when we take the derivative again, we'll have minus pi squared n squared over L squared times the cosine of all of that stuff. You multiply down diagonals, alternating signs, but on the last row, because you don't get 0 here, what you'll have to do, we still have this 1 over L. We'll have e to the x times the cosine, and then minus is plus, that evaluation applies here. You subtract the product, the integral of the product of the last two, but you affix the previous sign. So if I subtract a negative, it's going to be positive, but then I have to affix the previous sign, so I still get a minus pi squared n squared over L squared, integral from minus L to L, e to the x cosine pi n over Lx dx. So this term, still multiplied by the 1 over L, needs to be moved over to the other side and combined with this other integral. We'll have one of these integrals and pi squared n squared over L squared of those integrals. We'll have to divide that 1 plus pi squared n squared over L squared off, and that will finally give us the integral that we seek. So moving this over to here and then dividing the common coefficient off, it's 1 over 1 plus pi squared n squared over L squared. And now we just have to evaluate this expression here. Once you get the hang of this tabular method of integration by parts, it's going to be the best thing ever. We still have this 1 over L. 1 plus pi squared n squared over L squared. If you plug in L here, you get sine of pi n, but the sine of any integer multiple of pi is 0. The same thing happens when you plug in negative L. So this term gives you precisely nothing. On the first term, sure, you'll get e to the L, but you'll get cosine of pi n after you cancel the L when you make the substitution. But cosine of pi n is negative 1 to the n. We subtract what you get when you plug in negative L. If you plug in negative L for the cosine, the negative will go away, and you'll end up with negative 1 to the n again. So clearly you can factor out a negative 1 to the n, and I don't know about you, but it feels like a hyperbolic sine coming on here. If I divide by 2 here and multiply by 2 here, I'll end up with a hyperbolic sine again. I'd kind of prefer not to have compound fractions in my answer, so if I multiply by L squared on top and bottom, I can get rid of some of these fractions. We'll have 2L, negative 1 to the n, divided by L squared plus pi squared n squared times the hyperbolic sine of L. Maybe I'll show you how to get the other sequence of coefficients, the bn's, using a computer algebra system like Maple. We can check some of our answers so far. A naught was 1 divided by 2 times L times the integral of, when you calculate the exponential function in Maple, you use the exp function. We're going to multiply that by 1 in this case. x equals minus L to L. And we have hyperbolic sine of L divided by L, same as we had before. For the others, it's 1 over L times the integral e to the x times, for the first one, cosine of n times pi times x divided by L. We're integrating from minus L to L again. And I would like to simplify this. Now, Excel isn't quite so smart unless we make certain assumptions or specifications to tell it so. It doesn't know that sine of n pi is 0. We haven't told it that n is an integer. So this term should go away entirely. Same thing with this term, which is multiplied by sine of n pi. That term should disappear from this planet. Now, the cosine of n pi we know to be -1 to the power n. And that should also replace the other cosine of pi n. The L should factor out. And if we distribute the e to the L, we'll have e to the L here, and only e to the minus L here, since we add the exponents. You can see now we can factor and -1 to the n out. And we already distributed this e to the L. And this gives us exactly what we had before, except we haven't replaced this with a hyperbolic sine yet. So let's call this sinh. And the compensation we must pay is 2 times. There. Those are the simplified coefficients. What about in this other case with the sines? We get a similar kind of messy computation where certain terms are 0 and certain terms are -1 to the n. So anything with the sine of n pi gets zeroed out. We have a cosine n pi on both of the remaining terms. We know that that is -1 to the power n. So we'll put that here, getting rid of cosine n pi, cosine n pi. Both of the remaining terms have an n times pi left over. We can factor that out. Have a -1 here. And the n times pi is now gone. I'll take out one more negative, making this into a plus and this into a minus. When we distribute, we'll have the numerator for a hyperbolic sine again. We'll have to pay a price of multiplying by 2 and dividing by 2 to end up with a hyperbolic sine, like that. So we have all of our coefficients now for our function. The first term was a constant. Let's define what our L is here. Let's make L equal to 1 for the sake of argument. The first term is hyperbolic sine of L divided by L. But then we have a sum of a bunch of other terms. First of all, we have these terms. Notice the coefficients are very, very similar. These terms get multiplied by cosine of n times pi times x divided by L. And then we have these terms, which I guess I don't need the plus here, times the sine of n times pi times x divided by L. Let's go from 1 to 10. And I'm missing a operation in here someplace. There we go. Too many parentheses. I'm going to plot the function g of x between -1 and 1. Let's see if we're lucky. We get something that looks fairly well right. We're expecting this to look like e to the x. I'm going to plot this set of functions, in which case you can see how far off we are. Equals and you can see our e to the x function is fairly close to what we have here. If we increase from 10 to, say, 20 in the approximation, it looks even better until we get close to the ends where we have the Gibbs phenomenon. Going to 100, those look very tight. You can tell that this is a very good approximation when we use n equals 100, and at 1,000 it's incredibly close. We'll probably have to do 1,000 terms in the sum at least, but there it is. We're getting a pretty good representation. Let's change this back down to 1,000 and this back down to 100. And let's see what happens if we go from -2 to 2. You can see what's going on here. Our function, the Fourier series representation, is periodic. It's constructed from these periodic functions. And so the function that you construct is periodic. It's not going to be equal to e to the x on the entire line, only between -L and L. You get a very good representation on that limited domain. We'll have to develop more theory later in order to extend our Fourier representation to the entire real line. A simpler way to view this, however, is that if En is orthogonal and not normalized, then the Fourier series is the inner product of u with En over the inner product of En with En, all times En. In other words, we can do the simpler inner products without having to write in the 1 over the square root of L, and then divide by 1 over L in the end, and divide by L in the end. Remember that V is the sum, as n goes to from 1 to infinity, of, let's say, an En, if in the limit as n goes to infinity, we'll take the difference between these two, we'll take the limit as k goes from 1 to n, a sub k, e sub k is 0. And we're going to assume that in this particular instance, the norm that we're dealing with is the L2 norm. So to calculate this L2 norm, you take the square root of the integral of this squared. We'll define the error to be the difference between v and the sum as n goes from 1 to n in the L2 norm. It's obvious then that if V is an inner product space, and En is an orthonormal sequence with V in V and V equals, in the L2 sense, the sum, as n goes from 1 to infinity, of V with En, En, then what happens to the error? The error goes to 0. There is something called Bessel's inequality, if you take these inner products might be complex valued in some settings. So this will be the modulus, the complex modulus, absolute value in complex domain. And the idea here is, if the En's are some orthonormal sequence, they're orthonormal, so they're normalized, these would be the Fourier coefficients. And we're generalizing a kind of Pythagorean theorem here, but we're getting an inequality. And there's a good reason for that. This orthonormal sequence doesn't necessarily span the entire space. So in R3, let's suppose I have some vectors that are at right angle to each other, E1 and E2. My vector V might not be in that plane, in which case these coefficients won't be enough to reconstruct the entire vector. We won't get the entire norm for V out of this in this case. You have to have enough of these En's to span the entire space. But if these are just an orthonormal sequence, at least you'll get something that is less than or equal to the norm of V. It follows as a corollary that in the limit, as n goes to infinity, what happens to these Fourier coefficients? Well, if the sum is bounded, and if you're adding up non-negative terms, and it's bounded, it has to converge, which means these terms in the end have to go to 0. A set S in a vector space is called total or fundamental if, when you take the span of S and you complete that, you get the total vector space. The bar is the closure of this set, which means you throw in all limit points. A space is complete if it contains all of its limit points. If you have a vector space together with an inner product, an inner product space. And if every Cauchy sequence converges to a point within that space using the norm induced by the inner product, the 2 norm, then that complete inner product space is called a Hilbert space. A Hilbert space is nothing more than a complete inner product space. The important theorem is that if this is a total orthonormal set on a Hilbert space V, you get something better than Bessel's inequality. You get equality. This is called Parseval's identity. Note that Parseval's identity is a kind of generalized Pythagorean theorem, if you will. You add up the squares of the lengths of the legs, and you get the square of the length of the hypotenuse, if you will. I'd like to talk a little bit about complex Fourier series. But first, I'd like for you to recall Euler's identity. E to the I theta is cosine theta plus I sine theta, which is easy to prove using power series. You can find the Maclaurin series of cosine and sine, and the Maclaurin series of e to the x. If you replace x by I theta in the Maclaurin series for e to the x, you can parse that out and end up with the power series on the right-hand side. Proof is very easy, and you should know it, so give it a shot. However, I'd like to point out something that follows from this. E to the negative I theta, because cosine is even, will be cosine theta, and because sine is odd, we get minus I sine theta, which allows us then to combine these. If I add them, I can derive the identity that cosine theta is e to the I theta plus e to the minus I theta divided by 2, which, by the way, is the hyperbolic cosine of I theta. And in addition, if we subtract them, then sine theta will be 1 over 2i times e to the I theta minus e to the minus I theta, which is 1 over I times the hyperbolic sine of I theta. If we now look at the old formula for a Fourier series, we could rewrite this as an plus the sum, n goes from 1 to infinity, an times e pi n over Lx I plus e minus pi n over Lx I all over 2. And to get to the bn's, you do the same kind of thing, but you subtract, and instead of dividing by 2, you divide by 2i. We can now combine various terms. You can see that we can combine the e to the pi n over L xi's. We'll have various combinations of the an's and bn's. And we can combine these negative exponents as well. We can rewrite that as an plus the sum, as n goes from 1 to infinity, cn e to the pi n I over Lx, plus, I'll write this as c minus n e to the minus pi n I over Lx. To give you a clue, we can combine these and this a0 by summing not from 1 to infinity, but from negative infinity to infinity. This will give you the negative terms, this gives you the positive terms, there's a 0 term. Why not include all integers instead? The complex Fourier series will have the form the sum, as n goes from minus infinity to infinity, of cn e to the pi n I over Lx. To calculate the cn's, we need to take the inner product of our function with e to the pi n I over Lx divided by the inner product of the e to the pi n I over Lx with itself. These we should calculate. The inner product of e to the pi n I x over L, pi n I x over L, keeping in mind that since these are complex valued, we need to use the sesquilinear inner product. It's going to be the integral from minus L to L, e pi n I x over L, e to the minus, because it's a conjugate, pi n I x over L dx. And since you add the exponents, this ends up being e to the 0, which is 1, and the integral is 2L. So our integrals, our Fourier coefficients, will be 1 over 2L, the integral from minus L to L, of our function times e to the pi n I x over L dx. Let's look at the example that we just did. E to the x between negative L and L. Let's see how that one works in the complex case. We'll have 1 over 2L, the integral from minus L to L, of e to the x times e to the pi n I x over L dx. You can see that we'll have this 1 over 2L coming along for the ride. When we add the exponents, it's going to be x times the quantity 1 minus pi n I over L. So we'll have 1 minus pi n I over L here. We'll still have e to the same thing, x times 1 minus pi n I over L, evaluated from minus L to L. When we evaluated L, we'll have e to the L. What's left at L is the e to the minus pi n. If you think about the pi n I, that's going to go to cosine of pi n plus sine of negative pi n, which is 0. So you end up with the cosine of pi n, which is negative 1 to the n. When you subtract, plugging in the negative L, you'll get your e to the negative L. When the negative L distributes over here, you'll have a positive pi n L. The cosine of pi n is again 0. The sine of pi n being 0, the cosine of pi n is negative 1 to the n. So we'll have negative 1 to the n. We'll insert a 2 and put a 2 down here so that we'll have a hyperbolic sign yet again. We'll have the Fourier coefficients as negative 1 to the n over, if we distribute the L, we'll have L minus pi ni times the hyperbolic sign of L. That gives us the Fourier representation, the sum, as n goes from minus infinity to infinity. Negative 1 to the n, L minus pi ni. The hyperbolic sign can come out of the whole thing. And then we'll have e pi ni over L times x. You can see that A0, which will be the same as C0, is still the hyperbolic sign of L over L. When n is 0, these go away. This becomes a 1. This will be a 1. You get sinh L divided by L. How does this correspond to the ANs and the BNs from before? We have to form combinations of those. Let's look at the analysis using our computer algebra system, Maple. I'm going to start by assuming that n is an integer. Let's start from first principles, as a matter of fact. We're dealing with the integral, or rather 1 divided by 2 times L times the integral of e to the power of x. Remember that in Maple, the exponential function is exp, not e to the power of. Doesn't give you the right values in that way. E to the power of minus pi times I times n times x divided by L, where x goes from minus L to L. And let's try to simplify that. You can see that we have this e to the power 1, which when distributed will have a negative e to the power 1 plus e to the power negative 1. We'll take one of those negatives out of the top and shove it through the bottom. And it looks like we have a hyperbolic sign of 1 on the top. I'll take this negative and put it through the denominator. And this e to the power 1 combined to make the 1/2 times all of the rest of this as a simple hyperbolic sign of 1. There. Those are the coefficients. We'll define our coefficients to be exactly, well, exactly this. Now, I want to simplify C of n times the Fourier basis element exp of pi times I times n times x divided by L. I'll assume here that L is 1. Plus the exact same thing, but when n is replaced by negative n. There's a certain kind of symmetry that should allow for some simplification of these terms. And you can see that we do get a little bit of simplification here, but we can do better than what Maple just did. I'd like to put the real terms together, for instance. This term over to here. Every single term has a negative 1 to the n, with a little tilde on there indicating that we've made an assumption that those are natural numbers. So I'm factoring out negative 1 to the n on every single term. Now you can see that e to the pi I nx plus e to the minus pi I nx is twice the cosine of pi nx by the Euler identity. So it's going to be 2 times the cosine of pi nx. And we can eliminate this other term. Similarly, the I and the n pi can be factored out of the remaining 2 terms. We're subtracting, and so we get 2i times the sine. So let me see, we already have this pi n. I'll put that out front. Same thing over here. When we're subtracting these exponential functions, we'll have 2i times the sine of pi nx, eliminating this other term. Well, I times I is negative 1, so we can get rid of the i's, and both terms now have a factor of 2, so we can factor the 2 out on both of those terms, giving our simplified coefficients in this form. Let's define our function now. It's going to be the sum of, oops, I want to go back and redo this. There we go. The sum of these things n equals, let's see, where should we start these? There's another term when n equals 0, but remember that was sinh of 1 divided by 1. So there's our function. Let's plot the thing up against the exponential function. Let's make the view go from -1 to 1, and the y will go from -1 to 4. Scaling is constrained. Num points equals 1,000. The colors will be black and red, except we need to have, of course, there. I guess we didn't need to go to 4 on the y. Looks like 3 should be good enough. And we can see that the Fourier series representation, derived this time using complex analysis, works just as good as when we dealt with only the real numbers. Let's see now. We can do better if we increase n a little bit. And you can see that we get a tighter approximation, still suffering Gibbs phenomena at both endpoints. If we go from -2 to 2 on the x, we might need to go a little farther up on the y, let's go to 6. You can see that the approximation is only good between -1 and 1. If you go outside of that interval, you end up with the function repeating itself. And that's because we are defining this using these sinusoidal functions, sine and cosine, and it's going to repeat itself one way or the other. So there we have it, a Fourier series representation on a finite interval -1 to 1, and illustrating all the benefits and also problems of the real case and the other methods that we've tried to this point.